Hi scientists, welcome to our video on secondary forces, what they are, why they're important, how they relate to chemistry. So let's get into it. You may have remembered an activity that we looked at last term where we were looking at solubility. So here we've got a glass of water with a layer of oil floating on the top. And we also have a lava lamp on the right hand side where you see the phenomenon of liquids that are not actually mixing with each other. And that kind of leads us into our work on solubility. So a few terms that we're looking at: intramolecular, intermolecular, and a polar molecule. We'll start with intramolecular. Intramolecular forces are forces within a molecule, and these are strong attractive forces. Examples of these include covalent forces, ionic forces, metallic forces, and we know that those as covalent, ionic, and metallic bonds. Intermolecular are forces between molecules. These are weaker attractive forces. Examples of those are dispersion, dipole-dipole, and hydrogen bonding, and we're going to be going into those in this video and hydrogen bonding in the next video. The last term is a polar molecule, which we've covered previously, and if you can't remember or are having trouble with defining these, just refer to the previous videos on that topic. So polar molecules are molecules that contain polar bonds, and they're asymmetric. Examples include water. So we'll expand on intramolecular. Now, intramolecular forces are forces within a molecule. And the reason why I've capitalized this A is to help you remember that intra, capital A, molecular forces are forces within a molecule. So that's the way that you want to try and remember that term. So an example are the covalent bonds that exist between the hydrogen and the oxygen atoms in a water molecule. So the intramolecular forces within this water molecule are these blue covalent bonds here and here. They're connecting those atoms together to make up the water molecule. Here's a Lewis dot diagram of the same thing. So the two bonding electrons here and the two bonding electrons here would be considered intramolecular forces. And then here we've got the valence structure, again just the line to represent the covalent bond. That's our intramolecular structure. These are strong attractive forces, okay? These are strong, they take a lot of energy to break. A large amount of energy is required to separate the intramolecular forces between the two hydrogen atoms from the oxygen atom in each water molecule. You're going to have to put in a lot of energy in the form of heat or electricity in order to break those. It can be done. You can turn water into oxygen gas and hydrogen gas. It takes a lot of energy though. So the next type of forces are intermolecular forces, and these are the new ones. So these are forces that exist between molecules. And again, I've kind of capitalized the E, intermolecular, and then forces between molecules. I feel a bit silly saying it like that, but that's how you remember it. So intermolecular forces. Now the first thing I want to emphasize is that these are much weaker than intramolecular forces. All of the intermolecular forces are weaker than their intramolecular counterparts. Now, as you go on with this topic, sometimes that concept gets a bit confusing, or it can be confused by students. So I just want to be really clear with it. Intermolecular forces are weaker. These are also known as secondary forces. So you might hear that secondary forces term being thrown around. If we go back to our water example, only a small amount of energy is required to break the intermolecular forces between water molecules. And that brings about a change of state. So that's turning liquid water into steam. Okay? And the temperature that's required is 100 degrees Celsius. So we've all boiled water before. Maybe you do the cooking at home. If you don't, maybe you should start doing that. But what is actually happening here? We're turning liquid water into steam. Okay? But on a chemical level, on an atomic level, this is what we're actually doing. That water is obviously made up of millions and millions of water molecules. Each of those water molecules is attracted to each other. There's a force of attraction which is signified by these dotted lines here that are connecting those water molecules together. Okay? Now what is actually attracting them? It's the intermolecular forces. Okay? There's a force between those water molecules that's attracting them together. And what are we doing when we're boiling water? We're breaking those. Okay? Because in liquid water, here's another representation of it. This one's a lot scarier looking than the previous one. The Mickey Mouse molecule looks a bit friendlier than this, but it's the same thing. It's just the diagram of water. Now, in a liquid form, these molecules are quite close together. Okay, so those intermolecular forces are holding those water molecules together to have a liquid. But when you're boiling the water, you're actually overcoming these intermolecular forces. So you're basically breaking them. So you're breaking this one, you're breaking this one, you're breaking this one, you're breaking this one here. There's 4 of them here. And that's going to cause the water molecules to separate. And in a gas, that's what happens. The particles get further apart from each other. So that's what we're overcoming. Okay? So the intermolecular forces here are relatively weak, whereas the intramolecular forces, so this covalent bond here, is strong. So a summary, considerably greater energy is required to separate the intramolecular forces between the 2 hydrogen atoms from the oxygen atom in each water molecule. So intramolecular forces are also called primary forces. They're stronger than the intermolecular forces, which are the secondary forces. So now that we've had a bit of a chat about what intermolecular forces are, we're going to go into a few different kinds. There's 3 kinds we're going to look at, 2 in this video and hydrogen bonding in the next video. So we're going to look at the types of molecules involved, the explanation of the forces, example, and a strength, which my face is carrying up. There we go, strength. Cool. So we'll start with dispersion forces. Now these occur between all molecules and they're the weakest of all the intermolecular attractive forces. So we'll start with the weakest one. For the noble gases and non-polar molecules, these are the only binding forces. Okay? So when you think dispersion forces, we're thinking non-polar molecules. Okay? Non-polar molecules exhibit dispersion forces between them. Now this is where it gets a little bit tricky, okay? So I'll go through this with you, and then I'll explain it with a diagram. So dispersion forces result from the constant movement of electrons within atoms or molecules, and the interaction of molecules resulting from their own random movement. In both of these circumstances, temporary regions of partial positive and negative charge are created within the atoms or molecules. So for example, they become polar for a brief instant in time. These charge shifts result in instantaneous electrostatic attraction between the newly dipole molecules. The rapid and constant movement of atoms and electrons means the direction of these random interactions is constantly changing, creating a net but weak force of attraction between all the particles. So what does that mean? Here we just have a simple atom. We've got the nucleus here. We've got an electron cloud. So basically, if you've got an electron here and an electron here, you've got uneven distribution of the electrons. Okay? So what that means is that the electrons, which are always kind of moving around, orbiting in their clouds, at a certain snapshot in time, so freeze frame, we've got electrons on the left but not on the right, okay? And that creates a temporary or an instantaneous dipole. So if you take the snapshot of that, basically that's saying, alright, at this point in time, it's negative on the left, positive on the right. So there's a bit of a dipole created there. So remember, a dipole is a region in which you have oppositely charged ends. So negative and positive. Now here we've got another helium atom. So we've got a temporary dipole forming here, where you've got negative and positive here. Okay, so it's the same thing. And basically those opposite ends will attract each other. Okay, but then, fast forward a second later and the electrons have moved and the positives and negatives have cancelled out or moved somewhere else. So these kind of attractive forces are only happening for the smallest period in time, and then everything changes and then they're attracted in a different way. So it's very kind of all over the place. Now, the bigger the electron cloud within the atoms, the stronger the dispersion forces. Okay, so basically, bigger molecules, more electrons, therefore stronger dispersion forces. So to summarize, and I'm just going to move my face again, we have dispersion forces. They occur between non-polar covalent molecules. Explanation is here. An example might be a methane molecule, and the strength of dispersion forces is weak. So guys, we'll leave that video there, and next time we'll look at dipole-dipole and hydrogen bonding. Thanks for watching.